This video is sponsored by Kioxia. Solid-state drives are fascinating, not only because they can store terabytes of data, but because they can access any piece of that data almost instantaneously. This solid-state drive can hold 8 terabytes of data. If each bit were represented by a penny faced either heads or tails, that is, a 1 or 0, this drive could store the capacity of 64 trillion pennies. Now, if we laid all of these 64 trillion coins out flat on a surface, the area of the surface would take up the entire state of Massachusetts, which is an incredibly large area to be covered in pennies. But what's truly incredible is that the solid-state drive can find a 5 by 5 meter area of pennies anywhere on this massive surface, and then write to or read out the binary state of those pennies. In fact, the SSD can erase and change the state of every single one of these 64 trillion coins up to 10 times every day, and it can read out the state of all of these pennies around 70 times a day. So how does it do it? Well, in this solid-state drive, there are 18 NAND flash microchips that are used for storing all 8 terabytes of data. When we look inside a single chip, we find that there's a stack of 8 die. Each die has 2 planes, and if we were to zoom in on a single plane, we would find that each plane is a vast array of vertically stacked charge trap flash memory cells organized into thousands of blocks. Each block is organized into hundreds of pages, and each page contains tens of thousands of memory cells. And each charge trap flash memory cell can hold 3 bits of information, or 3 coins worth of data. Here's a nanoscopic picture of what the stacks of memory cells look like, which is just one microscopic section of the overall die. In other episodes, we discussed how information is stored in each cell, or how the pages of cells are organized. But for this episode, let's focus on the big picture and see how this solid-state drive can store 64 trillion bits, and how it can access or write to the contents of just one page of about 10 million pages. Note, however, that these numbers are approximate, and that they're different for different brands and sizes of SSDs. In this solid-state drive, there are a number of components we have to look at. First, over here, is the SSD controller microchip, or brain, whose role it is to interface between all 18 NAND flash chips. This microchip also interfaces and communicates with the laptop, computer, or server that the SSD is plugged into. Aside from the 18 NAND flash chips and the controller, the other main components are the 8 DRAM chips, which serve as a memory buffer for holding the massive lookup tables or translation tables that tell where all the information is stored. We'll get into what this lookup table does shortly. But for now, the other main components are the memory channels that allow the 18 NAND flash chips and the SSD controller to communicate. Each NAND flash chip has a memory channel and is composed of 16 wires or traces that run through the PCB. These memory channels are used for reading the address of where data is located and transferring the actual data to write to or read from the NAND flash. Additional traces are used for sending commands to write to or read out the information to each of the NAND flash chips. To better explain the data flow, let's use a simple example. The computer requests a small piece of information from the solid-state drive, say a picture. The SSD controller then sends the request for the NAND flash chip to read out the contents of chip 9, die 4, plane 1, block 351, page 45. The 3D NAND flash chip accesses that location and sends the contents along the memory channel's 16 traces back to the controller. This controller then routes the information to the computer that it's plugged into. Or the reverse could happen, wherein the computer asks to store data. The SSD controller would then ask the NAND flash chip to write the information to a particular page, or if the file were larger, the controller would write this file to hundreds of pages instead of just a single page. You might wonder, how does the controller keep track of where all the information is stored? Well, that's the role of the lookup table or the translation table. From the perspective of your computer, the SSD is just a massive set of sectors of data, each the size of 512 bytes. And thus this 8 terabyte drive has 15 billion sectors. For example, when you store a picture, your computer tells the SSD to store the picture's data in a set of unused sectors. The SSD controller then takes the picture's data and sends it, noting the address for the chip, die, plane, block, and pages of the precise location. The SSD controller essentially has a massive spreadsheet where all the sectors are translated into different locations inside the 18 different NAND flash chips. Note that this type of translation is also called a logical to physical translation, where your computer only sees what sectors the picture is stored in, but the SSD knows the physical locations. Furthermore, the translation table, or lookup table, is continuously being updated. When it's in continuous use, it can be found in the working memory, or DRAM chips, of the solid-state drive, and when it's not in use, it's saved to the 3D NAND flash chips. Another important detail is that while individual pages can be written to or read from, it's more common for superpages to be utilized. A superpage consists of all the pages on each of the 18 chips that share the same die, plane, block, and page designation, and thus the superpage has the same address in each of the respective 18 NAND flash chips. For example, when a large video gets saved, it gets spread across all 18 NAND flash chips and stored in a superpage, or possibly multiple superpages. Thus, when writing to or reading out the video, all 18 chips are running in parallel, resulting in read or write times faster than if the video were stored in just one of the NAND flash chips. Furthermore, superblocks can also be utilized, and they're the common block address among all 18 NAND flash chips. Also note that the SSD controller performs other functions like wear leveling, garbage collection, and executing the error correction code, but these topics will be saved for a future video. This is the fourth video that explains how solid-state drives and 3D NAND flash work. This video focuses more on the SSD architecture, while the other videos explain the structure of the 3D NAND flash, how information is written to a cell, and how information is read from a cell. Check out those videos as well. This video is sponsored by Kioxia. As you may have noticed, this is a Kioxia SSD, and there's a lot of engineering that goes into it. Kioxia sells a wide variety of SSDs, and the one we're using here is a data center class SSD, which is designed for consistent performance and latency for hyperscale applications. They also provide enterprise SSDs, which are top-of-the-line SSDs in terms of read and write performance and reliability. Check out Kioxia's SSDs using the link in the description. We'd like to thank all of our YouTube and Patreon sponsors for helping us build these in-depth engineering explanations. You can also provide your support by subscribing, liking this video, commenting below, and sharing this video with others. This is Branch Education. Thanks for watching.